Swayam Prabha. Digital India. Educated India.
Good morning everybody again, and let us continue our discussion on the fabrication of micro cutting tools. In the last class we have seen that there are many processes available which can machine a micro tool at the micro level with a diameter of less than 50 micron also. And we have seen that there are grinding process available, and after that we have seen the ultrasonic vibration grinding, so that we can reduce the forces on the cutting tool and we can get the very fine features on the surface. So, let us continue further in our discussion on fabrication of micro cutting tools. Then there is one process that is called wire electrode discharge grinding process. So, this particular thing is called wire electric discharge grinding. Right. So, you can get the tool diameter less than 100 micron also, because now we have seen that electric discharge is a force free, and earlier grinding it is actually the mechanical contact. So, even though it is a small contact or whatever the way you are using a fine diamond grit or anything, but still there is a physical contact. So, wherever there is a contact you always get some type of vibration or some type of bending onto the workpiece, and that is enough to break the cutting tool. So, this non-conventional process is all called the advanced machining processes, EDM, electrochemical machining, laser beam machining, electron beam machining. So, those things are very convenient to use in this particular domain, but we can see we can also tell that these processes are comparatively slower compared to the mechanical machining processes, and that is also one of the reasons that why mechanical micro machining is very important compared to the conventional micro machining operation, that advanced machining operation like EDM, ECM and other processes. So, here you can get the diameter less than 100 micron. So, what way we can do it, that this is the high speed spindle which we can directly use for fabrication of the cutting tool, and this is the copper foil, because this foil is required to complete the electric discharge circuit. Chuck is there, so by chuck you can actually hold the electrode and then you provide the wire guide here. So, instead of a normal cutting tool we are using a wire here, and that is the reason we are using it, we called it as a wire electric discharge grinding. And we tell it grinding here because what we are doing, that we are actually doing some type of cylindrical grinding type of operation here, and you can get the different type of geometry on the part. So, here what we are using, the copper diameter they are using with a 0.15 millimeter diameter, 150 micron is the diameter, and workpiece material is the tungsten carbide. And there are two different steps available, one is the rough EDM and another is the fine EDM with the different polarities. Why we do different polarities? Because now for a rough EDM what we are doing here in this case the workpiece what we are using, that is actually the positive one, because that is what we want to remove more part, and the wire what is here, that is the negative part. So, we know that in EDM whichever electrode is connected with the negative terminal, it will wear very less compared to the positively connected electrode. So, while doing this thing what we do, that we actually quickly remove the material and reach to the some type of particular shape. And once you want to get the fine EDM, then what we do, that we actually move this thing to the negative, because now we do not want to remove more material from the workpiece, and this will become the positive. Let the wire be wear very fast, because we are not worried about that particular wire quality or wire condition. So, here what we are doing, that by making this thing the material removal will be very less here, and you can actually finely tune the different features onto the surface. Right. So, this is the way it is happening. So, here what is happening, that this is the rotation. So, initial stage what we are doing, that we are doing rough EDM process. So, we are reducing. So, initial diameter was something like this. So, this was the initial part, and after that EDM, then what we are doing, we are making this particular shape. So, this is the shape after EDM or the rough surface or the rough machining. And once this part is over, then what you can do that you can stop the rotation here, because we want to create some features on the top on this side. So, if you look from this particular thing, then your initial diameter is this much when you are looking from. So, this is the bottom view of the cutting tool, and then what you do that you create some type of features on the top. So, now whatever is the thing here, what we are doing now, that we are cutting something like this. So, now this part will be away, and then this is the shape of this part or shape of the cutting tool, correct. So, now if you are rotating in this direction, then this will be a cutting edge, and if you rotate in the opposite direction, this will be the cutting edge. So, now we are stopping this part, and now what we are doing that again the same wire we are using, and then giving the shape in one direction. Now, you can see there is an offset between. So, here material is more and here material is less at this location. And then what we are doing then we are creating one slot here. So, now what is important here, that this slit is playing important role here. Now, if you look from this particular grinding wire and wire guide, this is something like this. So, this is the wire guide, and wire is located on the top of it. So, wire is coming something like this. So, wire is coming on the top of it something like this. Now, if you see, if you do this particular thing, then what is happening, that suppose this is your cutting tool, and we know that wire diameter is 150 micron and our cutting tool diameter is almost 100 micron. So, this is our cutting tool. Now, what is happening, that when you are plunging in this thing direction, then what is happening, that you are actually cutting something like this, correct. So, whatever is the diameter of this particular guide is that their diameter will be reflected onto the cutting part. So, we do not want this type of curved surface. What we need, that we need something like this part. So, we have to make sure that wire is straight here at this location, and that is the use of this particular slit. So, now how this slit will create this wire. So, now what is happening, that our thing is something like this. Right. So, this is the slit by which we are making the thing. So, now when your wire is rotating from here, at that time it will straightly go from here to here, correct. So, now you are reducing this particular curvature here, and now you are getting a straight wire. So, now your tool is here, suppose. So, now your tool is here, and your tool will actually give a similar cut here, because now this straightness, whatever is the same straightness will be created on this particular part. So, once this operation is over, now we know that we do not want to remove the rotation, okay, because if you rotate the thing, you will not get the same surface again, because that is also a problem. So, now what we have to do, that we want to cut similar thing from here to here also, this way. So, now what is happening, that this particular slot will be little bit big. Right. So, we have to make this particular slot little big. In such a way that once you complete this part, then what you have to do, that you have to move this particular cutting tool into this particular slot. So, now your cutting tool will be here at this location. So, your cutting tool is cut down something from here, it is cut down, and now your shape is something like this. And then you move your cutting wire guide in this direction, or you are cutting in this direction. So, this other portion which is curvature at this location, that will be also cut down. So, finally, what you are getting something like this surface. And so, this curvature will remain with, that is the whatever the diameter is there, but you will get two flat surfaces here at this location and this location. These are the two flat surfaces, correct. And then you remove this thing. So, after doing this thing, whatever you move this thing up, and then you enter this particular tool into that slit, whatever is small slit available here, and then do the, now wire is located in this direction. So, now it will do removal of this particular portion, whatever is available. So, it is cut down from this part. So, by this way, what we are doing, actually we are actually reducing the error because of the different type of motions. because now see that even if it is rotated at 1 degree here, then what is going to happen, that these two faces will not be parallel. So, you one way you will get something like this, another way you will get something like this, correct. So, that is the problem if you do not actually provide this type of facility, so that you can get the two faces machine without changing the setup of that. So, now advantage that now your whole setup is ready, and now you can do the machining operation without any problem. Right. So, this is the tool what we were discussing. So, now you can see that it has a two flat surfaces. So, this is the one flat surface and this is the another flat surface, and then it is doing cutting operation, but still you can see this is a negative rake angle, and that we have discussed many times that whenever there is a negative rake angle, you are end up with the very high amount of flowing phenomena, and this is the diameter and this is the width of that cutting tool. Right. So, this is the features which are created. So, width is the 40 micron is the width, and the depth this particular D is the 110, that is the total depth of the cutting tool. And what happened, that they did some experiment with a different type of wall thickness. Now, you can see here the feature which is created here. So, tool is passing through, and this is the wall thickness. So, initial stage your tool is moving from here and then it is passing from here, at that time it is maintaining this. So, you can see the wherever wall thickness is more, it is mostly straight and it is getting the whatever required dimension. Even the same thing here also. So, this is also acceptable, this is also acceptable. But when it is become more and more thin, what is happening, that the material do not have so much of strength in that. So, when you are cutting from here to here one direction and then you are entering here, because your material do not have so much of strength, then it will bend actually, and because of bending you will not get the required features, these things. So, by this particular experiment they found that this is the minimum wall thickness which you can get for a particular application. Why these type of things are important? Because these are very important in some type of, we can say, micro heat exchanger, right. Why it is important? Now, suppose consider that you have a surface here and you are some fluid is passing through this part and you want to cool this particular fluid, right. So, when it is passing through that, and this is the conventional tube kind of thing, something like this. But now, if you see that if you want to make very more cooling type of thing, then what you can do, that you actually create some type of features here onto the wall of the heat exchanger tube. Right. So, what we have done, that we have done some machining here. So, at that time you can actually do. So, now when you are passing the fluid here, now here it has a high amount, more amount of area. So, now if you increase the total area, then what happens, that your heat removal will be very fast from this, because here you are not getting same amount of area, and we have seen into the scaling effect that when you scale down the system, your volume actually goes down very quickly compared to the area. So, here you will get more amount of area. So, your the heat release will be very high compared to the other bigger size of component. So, there are different other areas also available where you need a very thin wall structure for different applications, right. So, another process is called focused ion beam sputtering operation. Here what we are doing, that we are using one ion beam as a tool for cutting different type of materials, and we have to use a 5 axis or 6 axis table in such a way that you can rotate your tool in a different direction to get the cutting at a different faces of the cutting tool. So, why this is important? Because it can give a precise control over the feature size, permits a variety of tool geometry, and establish the sharp cutting edges. So, these are some of the advantages of going with this particular process. Another advantage, the beam diameter you can go with a less than 3.5 nanometer. Why this is important? Because now you consider this much whatever this dimension, this diameter you consider the cutting tool, because ultimately you are cutting something. So, if your cutting tool itself is a 3.5 nanometer, then what is happening, that formation of the micron size feature with a nanometer precision is possible, and our energy level is extremely high. So, you can even cut the single crystalline diamond material. So, hardness is not an issue, and you have very fine size of the or very small size of the beam diameter, and that is advantage that micron size feature with the nanometer precision you can easily get. So, that is the advantage of going this with this particular process. But what is the problem that you can see this graph again. Now, whenever your beam is interacting with the workpiece, what is happening here, that it is starting cutting from this location, right. It is cutting here, and then gradually it is going down, and it is cutting completely this particular component. So, whatever this location is there, this location is coming into contact with the beam for a longest time, right. As soon as cutting is over, then you are switching off the supply. So, this is the location which is interacting with the lowest time. So, this is the lowest interaction time with the beam. Interaction time with the beam, and this particular location has the highest interaction time. So, when it is highest interaction time, what is happening, that you are getting here at this particular location very rounded edge. So, now this particular edge is rounded edge. So, this is what we are telling. So, this is the diametrically round. So, now if you rotate it this location, then this will be the rounded edge, and once you complete the operation, wherever the beam is coming out, these particular edges will be sharp edges, right. So, you have to rotate, or you have to kinematically arrange your workpiece in such a way that you at least get 1 or 2 sharp edges in such a way that you can remove the material very efficiently in this case. So, let us see that which way we can do this particular movement of the cutting tool, right. So, here what is written, the edge of the facet formed by the iron beam closest to the iron source is rounded mainly due to Gaussian distribution of the beam. So, that is what is happening in the left side, and the sharp cutting edge is produced at the far side. So, whatever side which is actually away from the beam and which is coming into contact at the last location or the last time, at that time those things are very sharp compared to that part. So, now what we have to do, that we want to create a one single point cutting tool by this particular focused band beam operation. So, this is the different movement of the cutting tool, so that we can get the sharp edge out of this particular operation. So, what is happening here? So, now here what is happening, that when beam is coming into contact, this particular edge is the rounded edge. So, let us color it red. So, this edge is the rounded edge, and this particular edge is the sharp edge. So, this is the sharp edge, correct. So, after that, the next operation is, now you rotate the workpiece. So, now what we are doing, that this particular edge is the sharp edge, right. So, now you are actually rotating into this direction. So, we are rotating this thing as a 90 degree. Now, we know that this is the sharp edge, right. So, this edge is the sharp edge, and earlier this one was the rounded edge, but now when it is cutting from this, so this will also become sharp edge, but this is the round edge now. Right. So, after that we again rotate into the 90 degree, then what is happening, that now you are getting a sharp edge at this location also, right. So, we have rotated further in this direction. So, now you have sharp edge here, you have sharp edge. So, this whole is a sharp edge, and this is a round edge at this location, correct. And then what you do, you little bit tilt in this direction right now, because what is happening here right now, that this particular face is completely flat face. So, this surface is at the same location, this is the flat surface. When you look from this direction, you are getting surface something like this. So, now we have to create a cutting edge. So, now if you see from this direction, what we are doing, that we are cutting this particular face here, right. So, the angle will be from this to this direction. So, this will be angled away. So, if you rotate at this direction a little bit, then what is happening, that what we are doing something like this. So, beam is always perpendicular vertical direction. So, it will cut down this particular portion from here to here, and you will get a single point cutting tool something like this, right. So, this whole edge will be the sharp edge in this particular part, and these are the edges which are rounded, it will not participate in material removal. So, you do not worried about that part. Right. So, this is the fabricated cutting tool. Now, you can see that this is the this dimension is 100 micron, this is around 25 micron or something, and this is all the things, it has a rake face, then it has a clearance face and other things also. And this is the side view when you look from this part. So, this is the clearance face available. So, you do not get any type of contact with the workpiece surface, and these are the clear face, this rake face, side clearance face, this is the clearance face, and diameter is the size is around 20 micron. So, now once you get this tool, then we have to actually operate this tool for the different operations. So, they did some experiment on the aluminum material, and this is what is done here. So, what is thing here, that this particular whatever is this width is the width of this, then they actually did some type of machining in this direction. So, once machining is done in, then after that they did machining in this direction. Right. So, by doing this thing, they are getting a different type of pillars on the workpiece material. So, here objective is that you get some material here, then you can use this thing as a for embossing purpose also, or you can use as EDM tool for creating some type of multiple holes onto some type of filter application or something. So, there are many applications of this particular type of features. And other than that, so here the pillar size is the 10 by 10 micron is the depth is, or that means height is the 20 micron, and the pitch is the distance between these two is the 30 micron. So, mostly it is the width of this cutting tool. Other than that, they also did some experiment with the thin foil fabrication. So, here they are not giving the vertical and the horizontal cutting, only one direction it is given, and then they did measurement on the what is the thin wall things. So, here the thickness of this particular wall is 10 micron, height is 20 micron, and this groove width is 30 micron. So, pitch and groove width is mostly depend on the what is the minimum width of the cutting tool which you are using, and that we have seen that smaller the size of the cutting tool, smaller you can get the width of this particular groove as well as the pitch of this particular features what we are creating. So, this is the way of fabrication of the single point cutting tool. Other than single point cutting tool, they have also fabricated end mill cutter. Right. So, these are the different end mill cutter, and we can see that the diameter is 25 micron, and we have seen that creating helix angle is sometimes very difficult, or even if it is possible, your rigidity or the strength of the tool will be sacrificed. So, that is the reason that these are the some three different tools are there. This is the two edges tool, this is 4 edges tool, and this is the 6 edges tool. 1, 2, 3, 4 and 5 edges tool. So, here this is the sharpness of the cutting edge of the 4 sided tool. So, here this is the, you can see that how sharp it is there, and then they did some experiment on the aluminum alloy. Now, you can see the lot of burr formation is there, because we know the aluminum is very ductile material, and when you do not have a sharp edge here, and we have seen that there is it will create a plowing effect and some type of rubbing effect, and still if you continue machining, then this is the burr formation. And what we have to do that once you get this thing, then you have to apply some deburring operation very gentle, so that it should not damage these particular features, but it will remove the burrs from the surfaces only. And this is on the brass machining, and brass also you can see the burr formation is not as large as alumina, but here you still get some burr formation, and that burr formation is creating problem at the later stage when you want to use this particular workpiece or this particular micro machine component for different type of applications. So, this was done with the 5 cutting edge tool. Now, coming to the EDM, because we know that we have already seen one example, that is called wire electrode discharge grinding, but EDM also you can use here. So, here what is done here, that micro EDM and micro grinding arrangement are on the same machine for the polycrystalline diamond material. So, now what is advantage here, that now first you do the fabrication of the cutting tool. on the without changing any type of machine setup. Now, there are two ways. Now, see that suppose you have a micro fabrication cutting tool, micro fabrication of the tool. This is the one setup. Setup 1. So, once you get this micro tool, then what you do, that you do a machining operation, right. So, now this one is the second setup. Now, what is problem with this particular methodology, that when you are cutting something here, that suppose your diameter you are getting something here and this is your cutting tool, this is what you have fabricated out of this particular process, and after that you are removing this thing and then you are mounting onto this particular part. So, now when you mount it, so you are actually shifting the location from the one machine to the other. So, you are actually relocating cutting tool to other machine or setup. So, what are the problem here? The problem is the run out, or suppose you are not actually fixing the properly, then it is a problem. So, error due to tool holding or because of the improper handling and many more here. So, what is our objective, that if you can do something like that, you first complete this particular machining operation by EDM and do not change the spindle, that you use the same setup and just move your cutting tool to the other setup where you can perform the grinding operation or the machining operation. So, what we are doing, that we are not shifting or we are not removing the cutting tool itself. So, whatever is the accuracy or whatever is the geometry you are getting here, geometrical accuracy, because we know that we have cut all the things by a reference of this particular axis. So, spindle axis and the tool axis are coincide perfectly. That will not happen, it may not happen when you are actually changing the workpiece setup. That means, you are using second machine and then you are transporting this particular electrode to the or the cutting tool to the other setup. But if you do everything in a single setup, that you can actually avoid many different type of tool holding related errors and you can get the run out very less in this case. So, this is what is the setup available. So, here what things are there, this particular table is the EDM part, and once you complete that particular the EDM, micro EDM and this particular setup, then what you are doing, that you are just shifting the table, right, and still the spindle and everything remains same, and this is the machining setup now. So, what we are doing here, that without change, so this is called the hybrid machining or something like that. You are fabricating tool on the same spindle and then you are using that particular tool for machining without changing any type of setup, just move the table. So, you have two machine here, one is the EDM machine and another is the micro milling or the micro grinding operation. Right. So, these are the different shape of cutting tools. So, this is a circular, this is a triangular, this is a D type and this is the square one. Right. So, by this way you can fabricate different cutting tool and then you do operation here. By that way you can actually save lot of time in the alignment and the correcting the different type of that geometrical error also. So, you do not need to spend lot of time there, and you are making sure and you also sure that there will not be any type of problem in the eccentricity related thing with the tool holder to the cutting edge diameter. Now, coming to the laser beam. So, laser beam is also used. So, in this particular study they use the infrared yttrium ortho-vendetta type of laser, which has a wavelength of 1.06 per micron, and this is the way they have done. So, it is a single crystalline diamond they have used. So, in this cutting diamond by the laser beam, so this is done there, and then what they are doing, they are bonding with the under material. So, this way they are actually making sure that the cost can be reduced further, because ultimately this particular top portion is only coming into contact with the workpiece. So, by bonding that thing they are actually spending less time, less money into the fabrication of this part. Once the bonding is over, then they use the laser beam and then they navigate the laser beam at a different location, and then they get the different type of features onto the top face of the cutting tool. So, these are the two different type of tools they are making. So, this is something like the end mill cutter or something like a face mill cutter kind of thing. So, these are the cutting edges here at this location and this something like that, and this is for creating some type of cavities here. So, their specific application was the fabrication of some type of concave cavities. So, now the edges are something, all these edges are there. So, when they plunge it inside completely, then what it will do, that it will remove the material from the sides completely, but still it will at the center portion you will get a different features here, because we know that when we rotate this thing, at that time you will get the theoretically 0 velocity at the center, because r is 0 at that location and maximum at the outer periphery, but still they got some results here. And this is what is happening with the cutting edge. Now, you can see that this particular this figure is belongs to this first diagram, that the tool with the sharp edges, and this is the rounded edges with the 0.5 micron radius. So, what is happening, that this is the initial. So, how this tool wear is progresses with respect to the diameter of this part, that is what it is showing. So, by this way you can see this is the 10 pass, this is the 20 pass, 100 pass and something like that is happening here. And by this way you can see that after 200 pass, the most of the part or the feature or geometry of the cutting tool is reduced drastically. So, it is better to reduce the or change the cutting tool. So, let me stop it here and we will continue this lecture further in the next class. So, still there are 1 or 2 processes available, we will discuss this thing in the next class. Thank you very much.